Next up we have Christina Graves, Scott Holmes, and we have a third member. And they're going to be speaking on synthetic biology, inducing a thermogenic response to cold. No, I'm sorry. No, that's right. Inducing a thermogenic response to cold shock in the URK colony?
E. coli.
We should have made it easier.
Okay.
That's right.
So, E. coli.
Okay, so I'm Christina, this is Ms. Pecha, and Scott, and we're part of the inaugural Georgia Tech iGen team. Our whole team is about 13 members altogether. So this is our project, and I'm going to hand it off to Scott.
So there's this plant, the sacred lotus. It produces, to attract insects, it produces a heat response 15 degrees above ambient, 15 degrees above ambient. It's volatile, organic compounds, so insects come. And so we wanted to take that the protein that was responsible for that thermogenic response, AOX, and put it into E. coli. So AOX produces heat in the sacred lotus by shuttling electrons, oxidizing O2 in a non-ATP producing manner. So it dissipates the electrons, and that produces heat. And so we want to take this and put it into E. coli and to make a thermogenic E. coli. And what are the applications for this? Agricultural buffering system, maybe protect seedlings from cold shock. We also wanted to study the evolution of thermogenic systems and make in the future, make a system where E. coli would huddle together in biofilm, produce a biofilm, and huddle together to produce heat. So we need a genetic system. We have 3 components to our genetic system. We have a cold shock promoter, which is turns on when it's cold and turns off when it's hot. We have a targeting sequence to get our protein to the proper location, and we have our heat-producing protein AOX. And so how does OMP-A work? How do we get a protein to the membrane, to the proper location? Without OMP-A, there's the cytoplasmic expression. This goes all over the cell. And then with OMP-A, our AOX will be targeted to the membrane, to the outside of the membrane, and we'll get proper expression. And so I'll talk a little bit about the cold shock, how we're going to get our bacteria to produce protein only in the cold shock response. We go to cold shock protein, and that will cause our promoter, hit B, to recruit an RNA polymerase and cause the expression of AOX. So Matessa's going to talk about what results and modeling.
All right, to predict the temperature rise, like heat production, we actually use Poisson equation in E. coli and Laplace in agarose to model how much temperature rise we're going to see. Remember that this is a minimum condition, so we expected in the colony-based model, we expected a rise of around 0.1 Kelvin degree, which I know it does not sound a lot, but this was totally not insulated and in minimum conditions. That was done using MATLAB and analytical approach. Using computational approach, using COMSOL, we actually got the temperature gradient from E. coli to agarose. And even using COMSOL, we got it around the same magnitude levels of nearly 0.07 Kelvin. And the heat gradient was from E. coli to the agarose. This was actually our lab. It was fun working in summer, and we did all our experiments and all our modeling results in this lab, and used all the equipment there to actually make the thermogenic bacteria. Sorry. Okay, yeah, this was what Scott was talking about. So when we made 2 constructs, so when there's no OMP-A in the system, the MRFP protein is expressed all over the cells with no particular targeting. But when we introduce OMP-A into the cells, as you can see, it targets into the periplasm, and our protein, which is MRFP, which induces red color in the bacteria, expressed in the periplasm. So these were our results after introducing the AOX protein, and as you can see, the AOX layer actually overtakes the RFP control when cold shock is induced at 15 degrees Celsius, and there is more temperature rise in AOX than RFP, which actually corresponds to our predictions. And as seen from 25 degrees Celsius, there is not much of a change. Both AOX, both bacteria induced with AOX, and RFP controls go actually on the same scale because our protein is not cold. Our protein is cold shock, and at 25 degrees Celsius, the promoter doesn't act on it, so it remains the same. So that was the temperature scale. this was done from the baseline, starting at a particular value and how much it rises. As you can see, AOX at 15 degrees Celsius actually gave us a result of around 2.1 degrees Celsius rise in our bacterial culture. And as compared to that, you can see that RFP control at 15 degrees Celsius rises slowly than the AOX one. Also, we compared our bacterial growth because we proposed that the heating at micro scale might help in like higher growth percentages. So at 15 degrees Celsius, you can see the AOX, the green line, actually overtakes RFP and our control to grow faster than RFP. But at 37 degrees Celsius, the growth curves are nearly the same. Another way to verify results, we did the thermal imaging of our solid plates, and to check that we had two phases after 30 minutes. So as you can see here, the AOX, the plates should go in three parts, but after 30 minutes, AOX kind of retains its heat, but the LB media and RFP actually loses its heat. So in conclusion, for our project, we did like project design, modeling was done. Then we actually made our bacteria with the induced promoters and the proteins, and we did our results and experimental analysis to actually verify